So it's my greatest pleasure to open this year's Marshall Lecture. I've done a small computation, so this first lecture was 1946, and so this is the 74th lecture of the series. And my duty is to introduce our 2019-20 speaker, Professor Paul Milgrom. Paul is the Shirley and Leonard Ely Professor of Humanities and Sciences at Stanford University, as well as professor at both the Department of Management Science and Engineering and the Business School at Stanford. He's a fellow of the Econometric Society, a member of the American Academy of Arts and Sciences, a member and the chair of the economic section of the National Academy of Sciences. He won a large number of prizes, among them the 2017 CME Group MSRI Prize in Innovative Quantitative Application and the 2018 Carty Award for the Advancement of Sciences. As an economist, Paul is one of a handful of distinguished economists that, starting at Northwestern, introduced game theory as a tool to study and analyze economic problems, turning completely around the way economists think and handle economic problems and questions. In particular, Paul has made a crucial contribution to a wide range of economic fields, from auctions to market design, from contract and incentive to industrial economics, from economics of organization to finance and game theory. He is also an outstanding teacher as well as a revered advisor and mentor. In particular, for what concerns auctions, Paul not only changed the way economists think about auction and pricing, but has also had a direct and huge impact in the use of auctions in the modern economic world. He is the designer of the auction the FCC used to reallocate the spectrum and make it available to mobile carriers and broadband providers. But let me leave it to someone much more qualified than I am to tell you and explain what is behind all this. So without further ado, let me give the floor to Professor Paul Milgrom.
I'd like to thank Leonardo for that lovely introduction. It's great to be here again in Cambridge. It's been quite a few years since I've been here, and great to remember all those guys at Northwestern who did all that amazing work when game theory was taking off within economics. It was a wonderful time. I was originally, I had put as the title of my lectures, Auction Design for NP-Hard Resource Allocation, and I've inserted the word "and" here because I've decided to focus this a little more. I learned that each of these lectures is an hour, and I was thinking they were an hour and a half. So I'll be a little more focused. I'll introduce the subject generally and then talk in detail about many aspects of one particular hard resource allocation problem. One of the things that makes it particularly pleasing to do this is education is so very important. And in fact, Marshall himself said the most valuable of all capital is that invested in human beings. You wouldn't want to read the rest of that sentence if you were a modern thinker because it distinguishes between men and women. But we'll leave this part of the quote up and just speak of Marshall that way. So there are three new kinds of challenges in auction design, getting right into it, that are coming up now that some of my colleagues like Richard down here and others have been working on. And the first two have to do with this idea that many people think about auctions as sort of a way to discover an allocation in prices, market clearing prices. And yet, in many of the applications we're interested in, there are no market clearing prices. The assumptions that we normally make in our simple economic models that guarantee market clearing prices exist are not satisfied, and in fact, they don't exist. And also the computations, unlike our standard convex models where you can find an optimum by hill climbing, you in a convex world, if you're maximizing the concave objective function, just keep heading up and you eventually approach the top. In these more complex problems, that doesn't work, and more complicated computational methods are used, mixed integer programming is used in a bunch of them that we'll talk about soon. And constraint satisfaction, I'll talk to you about in a few moments. It'll come up. It's another computationally hard problem. Now, there are lots of examples of this. Recently, a favorite example of mine is the New South Wales fisheries, an auction that was conducted recently that was designed by a collaboration between government regulators and operations researchers and economists. This was important for, this is a cap and trade auction. The New South Wales was reducing the size of the fish catch. Some of the fishermen were going to have to sell their rights and go out of business because there was we had more fishing boats involved that were needed. That was a non-convex problem. The fishermen who were going out of business wanted to sell their entire catch or else none of it. They didn't want to go to even smaller scales. They either wanted to enlarge their scale or completely eliminate what they were catching. The Universal Service Fund in the United States, this is an auction, the Connect America Fund, as it was called, was an attempt to provide service to high-cost areas of the country. And there, the areas were defined in terms of very small areas, but no service provider was interested in serving only a small area. If you were going to serve an area in rural Kentucky, you might want to put a base station there if you were serving it wirelessly, or you'd provide a switching station if you were serving it by wires, or depending on what your technology was, you might want a collection of these things in order to cover fixed costs. And you couldn't really value one single area by itself. They had to be valued in combinations. That made this a combinatorial problem, which was considerably more difficult, and the methods that were used to auction it were not methods for finding simple market clearing prices. London bus routes, I don't know if it still works this way. This is one of the early papers in economics and combinatorial auctions. The red buses that go around London have, the routes were procured in a procurement auction by the city, and a bus service that wanted to service them would need to set up a facility, say a station where the buses operated out of and where the buses were maintained. It had, the stations had to be of sufficient scale for them to operate at low cost, but they had capacity limits as well, and they had to solve all of that, and that involves fixed costs in an integer program, and there may not exist market clearing prices in general. Electrical power similarly has, for the many people who have worked in that, has various kinds of non-convexities that are challenging and might mean that market clearing prices will sometimes fail to exist. And the computations can be more difficult than the simple computations we have in elementary economic theory. Another kind of complexity that comes up in these auctions is communication complexity. This has been a concern of mine recently. A recent radio spectrum auction that we're talking about running in the United States will have 14 spectrum licenses for sale in each of 406 areas. And a bidder with a business plan will want to cover many of the areas. They'll have anywhere from 0 to 14 licenses in 406 areas. So that's 15 to the power 406 different allocations that a single bidder might get. And so how does it, in those of you who've studied elementary economic theory know that in simple auctions, what you do is you say what something's worth to you. I'm bidding for this, it's worth $10. But if you're bidding for 15 to the power 406 items, you can't just list your values for all of the items. The communications that are involved are also challenging, and we normally can't optimize fully in those situations. We need to find procedures that work well and overcome the communication complexity challenges. So those are the kinds of modern challenges we're working on in modern auction design. And I had originally intended a lecture where I'd talk about a few of these things, but I'm going to talk about one particular auction that I was deeply involved with and is of historic complexity, and to show you some of the kinds of issues that are faced. And that is the so-called incentive auction, which was conducted in the United States in 2016 and 2017 that Leonardo alluded to, that was about reallocating radio spectrum from television broadcast use to mobile broadband use. And so I'm going to introduce this problem to you with a video that the FCC put together. It's a 2-minute video so that you'll know what the problem was that we were trying to solve. So here we go.
Electromagnetic spectrum, or just spectrum, is the huge range of wireless frequencies used for all sorts of different things. From X-rays to microwaves, garage door openers and baby monitors to broadcast television. Everything wireless uses spectrum. There's a certain part of spectrum that is particularly useful for various technologies. This spectrum is licensed by the government to different users so that the signals don't interfere with each other. Companies that run satellites, radio, mobile phones, and broadcast television all license different parts of spectrum. But what we want to really focus on is spectrum that's part of the Broadcast Spectrum Incentive Auction. The process for this auction begins in late 2015 and will involve the FCC buying some of the licensed spectrum from broadcast television and then selling it to wireless broadband companies. 5 years ago, the Federal Communications Commission, the FCC, proposed the idea for an auction in the National Broadband Plan. Congress authorized the FCC to proceed a couple of years later. And for the last few years, the FCC has been sketching out the detailed and involved rules for this first ever incentive auction. There are 3 interrelated components to this process. There's a reverse auction, where broadcasters will voluntarily decide whether or not to sell their spectrum rights to the FCC. Broadcasters will bid downward against each other to give up their spectrum. At the same time, wireless broadband providers will bid upward in a forward auction to buy that spectrum. Finally, there's repacking, a mandatory nationwide process where all broadcasters that stay on the air may be required to move to new channels. The FCC will begin the auction process later this year, with station applications to participate due by December 18th. The actual auction will start on March 29, 2016, and will take somewhere between a few weeks and a few months. After the auction is completed, likely in the early summer of 2016, the FCC will announce the results and everyone's new channel assignments. Why is this happening? It's to really address wireless industry demand for spectrum, to increase broadband availability in the country, and to generate revenue for a number of government initiatives. Because the difference between what is paid in a forward auction and what is paid out in the reverse will be kept by the government for these purposes. Who will it affect? In terms of the voluntary auction, nearly every station will get an opening offer to sell, but ultimately, the FCC is expected to buy spectrum in large markets, geographically adjacent markets, or congested markets where there are a lot of broadcasters. As for the repacking, that will be a mandatory nationwide process that could affect any station on any channel in any market.
Okay, so that was the problem that was being addressed. I was actually hired in 2011 by the Federal Communications Commission before the authorizing legislation was passed to begin the planning for this process, and I had an incredible team of people that I was working with, some of whom I'll mention later. But what I want to do is talk about the process of getting ready for this auction, and it's quite an involved process. The first thing we had to do, since we were considering reassigning stations to different channels, is figure out patterns of interference. So this was the so-called TV study, the first step in the process, where through a combination of measurements and theoretical methods, we determined for each TV station, if they were assigned to certain channels, what areas would they interfere on. So customers who lived in this area would find that their broadcast signal from this station couldn't be received because of interference from that station. Okay, so this study was done, and the interference patterns sometimes depended on what channel was being used. So this picture refers to particular stations on a particular channel, although for the most part, if stations were close, they couldn't be on the same channel at all, and if they were far enough apart, there was no trouble putting them on the same channel. So you can think of as a simplifying idea that stations which are too close couldn't both be assigned to the same channel. And the constraint was that, as a matter of custom, you would say that there was interference between two stations if more than 0.5% of the existing customers would suffer interference. as a result of the channel assignment. So that was the standard for what it meant for two stations to interfere. And once we had determined the interference pattern, this is a simplification in which we imagine, as I've said before, that it doesn't matter what channel you're assigned to. If you're too close, you can't be assigned to the same channel. In that simplified conception, this red channel here, it can't be assigned to the same channel as any of these salmon-colored locations there because of broadcast interference. This defines a graph where each node in the graph is a TV station, and each arc in the graph represents an incompatibility. It says these two stations that are connected by an arc can't both be assigned to the same channel without creating interference. And when we put that all together, we got a map of the United States showing the interference patterns. You can see they're particularly dense here east of the Mississippi, but there's a pretty dense set here in the west, in the western states as well. Now, there are about the co-channel interference, what I've described to you, where two stations can't be put on the same channel. There are about 130,000 such constraints in the US allocation problem. And it turns out that's not really a completely adequate representation of the problem because I said sometimes whether or not you can be on the same channel depends on the channel, and sometimes you can't be on adjacent channels either without creating interference. And some channels are reserved by the Mexicans or by the Canadians near the border, and they need to be treated differently. So we had to make a full list of which channel assignments would be incompatible. And the full list that we used had 2.7 million detailed constraints. So those were the constraints on the channel allocation during the course of the auction. And so during the course of the auction, if we said, well, I'm going to buy Richard's station and Partha's station, and so I'm going to buy a certain set of stations, and I want to know, am I going to be able to have enough channels left for the stations I didn't buy to assign them all channels without creating interference? I'd have to solve a channel assignment problem and ask, anytime I'm considering a set of bids, and maybe I'll take those bids, is if I take those bids and not the others, will I be able to assign channels to the remaining broadcasters? Now that's very similar to a problem that's a famous problem in computer science known as the graph coloring problem. The graph coloring problem asks, if you have a graph, is it possible to assign a color to each node, think a channel to each station, such that no two connected nodes are the same color, no two stations connected by an arc are on the same channel. In the simple representation that I described earlier, they're identical problems, and the graph coloring problem is NP complete. And some of you know what that means and some of you don't, but as a, roughly speaking, under one of the hypotheses of computer science, P not equal to NP, we won't get into that, but one of the standard hypotheses, if a problem is NP complete, then for any algorithm you create to solve the problem, there will be a sequence of problems of growing size such that the solution time grows exponentially in the size of the problem. That's a rough statement of what it means. And you don't want to put 2.7 million into an exponent on any number larger than 1 for your solution time. That would be disastrous. But what the computer science doesn't say, that, by the way, was my understanding of this at the beginning of this project. What the computer science doesn't say is that that's how long an average problem takes. It just says that there exists a sequence of problems that take a long time. And in fact, it's sometimes possible to design algorithms that on average run very fast, at least for classes of problems. And so we designed such an algorithm for this problem to speed things up. But this is an example of a very hard constraint satisfaction problem. And we had to solve one of these every time we considered a collection of bids that we might solve. We'd solved about 10,000 of these during the course of the auction. Okay, so for the incentive auction in particular, this was a dauntingly difficult, challenging problem. It was challenging for 3 reasons. First, the constraints were extremely complex. We have to decide the set of stations to buy, and the stations we leave behind, a set of stations S, we'll write S and F to mean that it's feasible for those stations to be assigned channels without creating interference. So that's the F will be the collection of subsets of stations that are currently broadcasting that can feasibly left on the air with the channels that are remaining available. And we have to assign channels to about 2,500 stations on the air without creating interference. So that was the first challenge. The second challenge that made this unusual is that this was a two-sided auction. And by the way, the first challenge is pretty much what I'm going to be talking about for the rest of the lecture today. The second challenge, which I'll talk more about tomorrow, connects more closely to Marshall's own work. Marshall talked about in his writings from 1890 how market clearing takes place by adjustments in quantity and so on, and I'll talk to you more about that. But this is different from Marshall's work in that the things that are being bought and sold are heterogeneous. Marshall looked at quantity adjustments when people were buying and selling all the same thing, but the things that that people are selling here, broadcast rights were all different. Somebody has a station in Chicago, somebody has a station in Atlanta, somebody has a station in San Francisco, and those are not the same things, and they need to all be cleared. Uniformly across the country, we need to clear the same number of channels in every area of the country. And second of all, we need in this, and by the way, on the forward auction side as well, when we're selling mobile broadband licenses, there are licenses for New York and Chicago and New Orleans and Houston, and they're all different things, but we have the same amount of spectrum available to be sold in all of those areas, so the quantity has to be decided. And we have to balance efficiency and cost objectives. We have to respect a budget constraint that the government has to be able to pay for the retuning of stations that stay on the air with net revenues generated out of the auction. And we have to keep the rules simple enough that bidders can actually bid in this auction, because this is a really complex process that's going on. And you might be, if your grandfather founded a television station in Topeka, Kansas, and your family owns it and wants to sell it today, that's quite a big deal to decide to sell the family business and give it up. And the process has to be one that the bidders would understand. So that was the set of challenges that we faced, and which I must say initially seemed extremely daunting. Now, I understand that most of the undergraduates haven't learned about Dickery auctions yet, so I'm going to say a few words about this. When I was hired in 2011, the FCC staff internally had decided that perhaps the right way to approach this was to run a Dickery auction to buy stations. And for those of you who don't know what a Dickery auction is, I'm going to tell you a little about it now. This is a reverse Dickery auction. This is an auction to buy. We usually you learn them in terms of auctions to sell, but it's the same general idea. So the idea is that the first thing you would do is you would try to choose the argument that maximizes the total value of the stations that remain on air. So you're choosing a set of stations that you're going to leave on air from among the stations that are feasible, sets of stations that are feasible, to maximize the total value of the stations that continue to broadcast. That was the conceptualization that underlies the Dickery auction. And you're going to call the set, the argument that maximizes this function will be called S star. Those are the stations that you're going to want to leave on the air. So you ask every station owner, how much is your station worth to you? The station owner in Topeka, Kansas says, my station is worth $10 million to me. You take all of your sets of stations and you find the combination that's feasible and maximize that. And then you set prices. I've graded these prices a little bit because I don't really expect that, if you haven't seen it before, that you're going to memorize this formula. But let me tell you what this formula says. It's about, you pay each station that goes off the air its opportunity cost. That is, you calculate how much value would you be able to get from stations if you didn't have to put station I on the air. And then you said, well, suppose you did have to put station I on the air. How much value could you get for the other stations if you did put station I on the air, and you take a look at the difference and say, that's how much it costs me, that's how much it would cost me to leave Station I on the air. I would get $15 million less if Station I were on the air than if I could take Station I off the air. So I should offer it $15 million to go off the air. You should offer it its opportunity cost. That's the idea of a Dickery auction. And if you do that, it'll be in each station's interest to report truthfully. You're offering them a price that has nothing to do with the report. If they say, you know what, my station is worth $10 million, then you say, great, then you'll take $15 million, that's what we'll pay you. And if they say my station's worth $20 million, you say, sorry, you know, your station's only worth $15 million to us, we won't take you. And that's how the Dickery auction works. This calculation is fundamental. But the problem with this calculation is that we can't do it. And the reason we can't do it is that these optimization problems are really hard. Just checking feasibility is really hard, and the optimizations are hard too. And this number is the value of about 2,500 television stations. And this number is the value of about 2,500 television stations. And if you made if you could optimize this to 99% and made only a 1% error in the optimization in, let's say, one of them but not the other, then you would be off by about the value of 25 television stations, average television stations. And that error would be in the price for one television station. So you need to be able to do 1,000 times better than that to come up. This is the difference between two large numbers. It's mostly noise. And we did some sample calculations. The sample calculations worked out really badly. We got a lot of nonsensical results, including negative prices, which make no sense at all. And all sorts of things went wrong with these calculations. So the first problem with the Dickery auction, the Dickery auction, by the way, is the standard in the literature. And the reason it's the standard is it's the only auction, it's provably the only auction that has the property that it's in everybody's interest to report truthfully, that it selects an efficient outcome, and that the losing bidders pay zero, are paid zero. It's the only auction that has those properties. Anything else fails to have some of those properties. So that was why it came up. It's been the standard in the literature for a long time. The first problem that it has is that we can't compute the Dickery allocation and prices. The second problem that we have, and by the way, I'm going to list 7 problems that we had with the Dickery auction and show you how we overcame all 7. The second problem is that it requires too much trust. So you're a station owner whose family owns a television station in Topeka, Kansas, and you barely understand these computations. How are you going to bid in an auction? Do you really trust that they tell you that you should report truthfully? Well, how do you know? How can you trust that? Remember, this is the government, and in the UK and the US, we don't have that much faith in our governments. And what makes this even harder is that the FCC has to say, well, they can't promise that their calculations are going to be accurate. These calculations are too hard for us. And by law, they can't share the data that you would need to check the calculations. That's people's private information about their bids. So we thought we might not get 100% participation with rules like this. The first rule of an auction is get the bidders to participate, and we didn't think this met that standard. Okay, so here are 3 more problems. So that's the first 2 problems, difficulty of computation and lack of trust. Here's 3 more problems with the Dickery auction, and I have an example here of 3 stations. Most of the major cities in the United States are located along water. So you can think of them as along some line, curved or otherwise. And so here I have 3 stations, A, B, and C. A and B are pretty far apart, and C is in between them. And I want you to imagine that initially, before I've run this auction, I have 2 channels available, and A and B are both using channel 1, and C is using channel 2. Okay, and the goal, however, is to take one of these channels out of service and go from 2 channels to 1. Just about the simplest possible example. Okay, well, what happens? If you optimize, if VA plus VB is less than VC, so these stations are less valuable, then you'll want to leave station C on the air to maximize total value, and you'll want to buy stations A and B. And if the inequality is reversed, then it'll be optimal to leave A and B on the air, and you'll want to buy station C. And when you go through and calculate the Dickery price, if station C stays on the air, then you pay it the value of station A plus the value of station B. That's the opportunity cost. You had to take stations A and B off the air if C wins the auction. And if A and B win the auction, their Dickery prices are VC minus VB and VC minus VA. And that just comes from calculating those differences that I described for you earlier. Okay, as this example shows, the Dickery auction has 3 more problems, numbers 3, 4, and 5 here. First of all, it's not budget aware. These prices have nothing to do with the budget that's available. And if the government doesn't have this much budget available, then the auction fails. And an auction that can fail is not a Dickery auction. You can't have rules that say, well, if the prices are too high, I'm going to cancel. Then it doesn't have the properties of the Dickery auction anymore. So it's not budget aware. It's not group strategy proof. If A and B are thinking, they might say, let's both bid 0. Then we can win, and we'll both get prices of equal to VC. We can collude and be both better off. That's group strategy proofness. And third, it's not generally price competitive. If A and B win, if you calculate the total price, their total price in this case can be, and often is, more than the value of station C. And station C says, wait a minute, you're paying $50 million to those guys to go off the air. I'd go off the air for $30 million and solve your problem. It's not price competitive. The loser says, I would take that money and I'll charge you less. So that's problems 3, 4, and 5 with the Dickery auction. Okay, so those are the first 5 problems. Number 6, we generally have an objective that balances both efficiency and cost. We're trying to keep the cost down because the government keeps the difference in revenue. And the Dickery auction requires that the winning bidders reveal their values. And that has been a problem in past auctions where bidders are not happy about having their values revealed, or the government's not happy. There's a famous story in Australia, actually, of an auction where it was a second price auction, and the government was selling, in that case, rights to access to a satellite, and the winning bid, the highest bid was $1 million, and the second highest bid was $6. And the government got some rather unfavorable publicity for that auction. So they don't like this information about what people are willing to pay to come into the public. Okay, so we are able to address all 7 of these problems in the auction that we actually ran, and I'm going to describe how that's done now. Okay, so I'm running out of time, so I think I'll just skip this slide and go on. And the auction we're going to run is going to be a descending clock auction. You'll see what it is in a moment, but I'm going to explain it to you first by doing an aside about computing the solutions to a hard problem, approximate solutions to a hard problem. Then I'll show you how the auction computes the solution to this problem. So I'm going to start with a classical problem. So here's our problem. Our goal is, given a current set of stations, find the feasible subset S star that should continue to broadcast in a more limited set of channels to maximize the total value. Vn is the value of station N. This is the total value of the stations in the set S. And we want to find the set S, which is feasible to pack, that maximizes that total. So we're trying to solve a hard optimization problem. Now, this particular optimization problem is very similar to a classic problem in operations research and computer science, and many of you may know, called the knapsack problem. It's a standard problem that we look at in this context, and it looks very similar. Here you're trying to select a set of items, some subset of the set you have, to maximize the total value of the items that you take But in this case, the constraint is that you have a knapsack, and the knapsack will only hold items that weigh in total no more than 20 kilos, and each of these items has a weight or a size, and the total size of the item can't make it bigger than fit in the knapsack, or the total weight of the item can't be bigger, or if it's a budget constraint problem, the total cost of the items can't exceed some constant. So this looks very similar, except that it has a simpler constraint, the so-called knapsack constraint. Okay, and for this problem, there is a standard solution. Now, this problem, by the way, is NP-hard. This is a problem that if somebody tells you, I know the answer, and here's what the answer is, and you have some general algorithm to check whether they've given you the right answer, your algorithm can take a long time to run in principle. Okay, there aren't any. This is a problem that if you want to check actual optimality, it's a very hard problem. But often this problem can be approximately solved very well, and here's an approximate solution that does really well in many contexts. It's called the greedy heuristic, and what you do is you order the items by their value per unit size. So the first item has a value of 10 and a size of 2, so its value per unit size is 5. The next item has a value per unit size of 4. You take them in that order, and what you do, it's sort of like, if you're going to sell a bunch of stuff at the county fair and you want to pack your trunk with the most valuable things, you take the things which have the highest value per unit size and you put them in first. And you do that until you have some item that doesn't fit, and you set it aside and put in the next item. This is called the greedy heuristic. It doesn't optimize, but it often does pretty well. The difference between the maximum value and the greedy algorithm value is at most some fraction of the value of the first item that's excluded from the knapsack. If you could take that first item that was excluded and cut off a piece of it and fit it in, that would be an actual optimum. So that gives you, that's the most you could possibly lose by using a greedy algorithm. So if the items are small, for example, relative to the size of the knapsack, this gives you a good approximation. So why am I telling you about greedy algorithms, and what does this have to do with auction design? So I'm going to surprise some of you by telling you that an auction is a greedy algorithm. And here's how that works. I'm going to show you an auction that exactly duplicates the algorithm I just showed you. And it works like this. Informally, this is an informal description. I'll get more precise in a moment. But informally, what you do is you have a clock that's running over a time interval 0 to 1, and it starts at a very high number, and it gradually falls until it finally ends at 0. And at every time in this interval, if there's still space for item J, what you do is you offer it a price PJ to go off the air. Here I'm trying to remove items and not put them in the knapsack. In this auction, well, you'll see what's going on here. I offered a price PJ to go off the air, and the price PJ is set to Sj times Q of T. That is, it's proportional to the size of the station. Now, what's going to happen then is I'm offering the same price per unit size to every station during the course of the auction. And as this runs, if Partha's station is worth 10 per unit size, if it has the highest value per unit size, I'll hit his price first, and he'll say no. You have to put me on the air. So the station that says no is going to go on the air, that is into the knapsack. Okay? And as I continue declining, bidders decide whether their offers are acceptable. And if there's no space for Richard's station over here, then I don't lower his price anymore. I say, I'm going to buy your station. I'm not going to put you in the knapsack. And so what's going to happen is that the stations that say no to their offers are going to be first the guy with the highest value per unit size, then the guy with the next highest value per unit size if he's feasible, and so on, going down the list. And the bottom line is that if bidders all bid truthfully, then the same bidders are packed on the air in the same order as in the preceding greedy algorithm. This is just the auction implements a greedy algorithm. So you have to keep in mind that what this is doing is it's implementing an approach to optimization that is an approximate approach that's well established in the underlying operations research theory. Okay? All right. So we're going to take a look at a class of these auctions. Instead of proceeding continuously, we're going to proceed in discrete rounds, so it'll be approximate in that sense. And an auction rule is going to be a function that tells me, depending on the history of bidder activity in previous rounds, which bidders have said yes and no, how to set prices in the current round. And the price that's offered to any bidder in a round can be no higher than it was in the previous round. These prices can only go down. The auction ends in the first round when no prices change. And every such function that satisfies these two constraints describes a different auction. So auctions are characterized, descending clock auctions are characterized by functions that tell you, based on the history of what's happened so far, what prices you should offer in the current round, subject to only reducing prices. Okay? And some of these auctions, by the way, use fast heuristics and are easy to compute. Some of them not, but we can solve the computational complexity problem by using a fast heuristic, and that's what we did, and I'll show you that in a while. So this class of auctions, and this, for those of you who are more mathematical, I don't have time to go over this slide. This says exactly the same thing as the previous slide, but it says it in mathematics. Okay, I have here are two slides again that say it in words and then in mathematics. This is a picture of Shengwu Li, who introduced the concept of obvious strategy proofness a couple of years ago. A strategy for a player obviously nominates another strategy. If whenever the recommendations of the two strategies differ at some point, at some information set, the best payoff that can follow from the deviation is no better than the worst payoff that can follow from playing the recommended strategy. So the idea is, I'll show you that actually in mathematics here for a moment. That says that the maximum over all the things everybody else can do when you're playing the deviating strategy is no better than the worst thing that can happen over what everybody else would do playing the actual strategy. And then a strategy is obviously dominant if it obviously dominates every other strategy. And here's the first theorem. And this is the theorem that solves the trust problem. In every descending clock auction, bidding truthfully is an obviously dominant strategy. So here's how it works for you. So Leonardo here is bidding in an auction, and his item is worth $20 million to him. And the auction opens with a price of $40 million for him. And we say, Leonardo, would you like to sell your station for $40 million? That might be your final offer. Would you accept $40 million? Well, it's obvious he should say yes. If he says no, the best thing that happens is he gets zero. If he says yes, the worst thing that happens is he's going to wind up with zero. So he says yes. He said, well, I'm sorry, I got more offers than I needed. I'm coming back now with lower offers to stations. Would you take $35 million? He says, well, yeah, sure, I'd take $35 million. It's obvious. The best thing that can happen if I say no is I get zero. The worst thing that happened if I say yes is I get zero. Must be optimal to say yes. When the price, what did I say, your station was worth $20 million? When I finally offer you $19 million, and he looks at it and says, well, I know prices can never go up, so the best thing that can happen to me if I say yes is I'll get zero. They won't buy my station. And the worst thing that can happen to me if I say no is I'll get zero, so I should say no. So it's obvious how to bid in this auction. And it's obvious how to bid even if you don't trust the computations. So even if the government is doing the computations incorrectly, and no matter where, even if they're pulling these numbers out of there, you know where, it doesn't matter. It's obviously dominant. The trust problem is solved. You know what to do, and it doesn't matter whether you trust the computations or not in deciding what your optimal behavior will be. So this is an auction that's very easy for people to bid in. It is group strategy proof. And I just got a text message from Shengwu Li, who seems, I don't know how he knows that I'm talking about him right now, but popped up on my watch. It's obvious. Okay. In every descending clock auction, no coalition has a deviation from truthful bidding that strictly increases all the coalition members' payoffs. Okay, how do we know this? Well, no matter, and this is true no matter what everybody else is doing. Well, suppose you, sir, are part of the coalition with these other guys in your row, and they say, look, we should all deviate, we'll all be better off. And during the auction, you're the first one that has to deviate. And you say, well, is it possible that I'm better off? Well, this game is obviously strategy proof, so no matter what these guys are planning on doing, I can't be better off to deviate, because that's what it means to be obviously strategy proof. So the first guy to deviate can't benefit, and so it's not possible that there's a group of people, all of whom benefit. Okay, so that proves group strategy proof, and that's the proof. So I've just shown you that these descending clock auctions can be chosen to compute quickly and well. I actually haven't shown you that yet, but I've argued that I have a big class, and I will show you that we've chosen ones that can compute quickly and well, that are obviously strategy proof and group strategy proof. Let's talk about budget constraints. How do we deal with that? Well, so I'm going to say, given an auction characterized by a rule for setting prices P, I'm going to talk about a budget-respecting extension of P with a budget B, and it's going to be defined as follows. It's really simple. I run the auction P, and when I get to the end, if I haven't satisfied the budget, I just keep the prices going down. That's what a budget-respecting extension is. You keep the budget going down until you do satisfy the budget constraint. Obviously, that satisfied the budget constraint, and it has the property that if the original auction would have satisfied the budget constraint, then you're running the original auction. So we can extend any of these auctions to something that satisfies the budget constraint, and you can't do that with a Dickery auction. A Dickery auction cannot be extended to satisfy a budget constraint. Okay? Theorem for every descending auction and every budget, there is a budget-respecting extension. I've just described to you how the construction goes. Okay, now this is the most challenging and difficult part here. This is how we are going to reflect both costs and efficiency in the same auction. How are we going to pursue both cost and efficiency objectives in the same auction? Now, finding the auction that minimizes expected costs, that's a classic problem in auction theory. Roger Myerson here won a Nobel Prize for his work on that problem. Roger considered the case where there was a single item for sale, and he found the revenue maximizing auction. It's the same thing to find the cost minimizing auction if you have a single item you're trying to buy. But here we have a more complicated feasibility constraint. But what Roger showed is that the expected payments depend only on the allocation. And that argument, it turns out, that the expected payments depend only on the allocation, that's completely general. It has nothing to do with the constraints. So for those of you who know Myerson's analysis, you will discover that if you, given a procurement auction that incentivizes truthful bidding, the expected total payments, you can manipulate them, and I'm not going to do his manipulation here, to write it as the expected sum of what are called virtual costs. And the virtual costs are here, and I will make them available for you offline. But the important thing to know is that that can be done. So we can, if we want to minimize our costs of acquisition, that's the same thing as minimizing the virtual costs of the stations that we buy, and that's the same thing as maximizing the virtual costs of the stations we don't buy, because we have a fixed set of stations. So we can write this as a maximization problem, where we're maximizing the virtual costs of the stations that are left on the air. And now we can find a greedy algorithm for doing that, and basically what the greedy algorithm does is it says, take the station with the highest virtual cost per unit size first, then take the station with the next highest virtual cost per unit size. And so we can have a rule for setting clock prices that sets the virtual cost per unit price the same, per unit size the same for every station at every point in the auction. And that leads to a greedy algorithm that maximizes the virtual costs of the stations taken off the air and minimizes the virtual costs of the stations that are left on the air. Okay, so we can find such an auction by, within our class by modifying the price rule. So we can do cost minimization, efficiency maximization, and anything in between. Clock auction prices are competitive. We never run into this problem of the Dickery auction. Given any descending clock auction P, if you, and any profile of values of the stations, if this is the set of winners and these are the prices they pay, then these prices that they pay, if they were to bid those prices in a simple auction and we were to use the same winner selection rule, that would be a full information equilibrium of the corresponding auction. And that's a notion of competitiveness. It says if everybody knows the prices and we're just taking the things that cost least using this winner selection rule, nobody would have any incentive to change their bids. Okay? So it says that the prices are competitive. And finally, privacy, and this is a subtle one that's mostly for the computer scientists. If we have, you know what, I won't even do this one here, but this is a characterization of descending clock auctions. If you are a winner in descending clock auction, Partha, congratulations, you just sold your station for $40 million. Nobody knows anything beyond the fact that you were willing to take $40 million. Anything beyond that, they don't know. And this is the unique set of auctions. In fact, this class characterizes the set of auctions that preserve winner privacy. That's what this says in mathematics. Now, the caveat down here, I guess I will say, there is the caveat's a minor one. I could have an auction in which I say, Partha, would you be willing to take $40 million? And you say yes. And I say, are you sure? And you say yes. And that implements the same allocation. So this says that anything that I can do by any rule, I can do by a descending clock auction. There are other rules that involve irrelevant communications that do the same thing, but there's nothing new added by adding any rules to these auctions. Okay, so recap. What I've shown for you is that we can do all of these things, and what I have still to show for you in the last few minutes is what we actually did do at the Federal Communications Commission. So we ran this auction in 2016 and 2017. The auction generated $20 billion of revenue and $10 billion of cost, and that's where we ended up. But here's how the auction was set up. The price that we offered each station at every round of the auction was given by this formula. We had this central clock, P0 of t, that was going down during the course of the auction. It was declining 5% around. And for each station, we would look at the population that station served and the number of links it had in the interference graph, and we took the population that it served to the power of 0.5 and the links in the interference graph to the power of 0.5. We multiplied those. Those are sort of, this one is links is sort of size, how hard it is to fit something in because it creates interference with lots of other stations. And this one, population, is sort of like going to virtual costs. It says if a station is not serving very many customers, I ought to be able to get away with offering it a lower price. And we put these two things together, and we had to explain, so that's size and that's virtual cost. And we had to explain to the regulators why we were doing this formula. So this formula, which wasn't exactly optimal, we said, well, a station that has twice as many pops and twice as many interference should be offered twice the price. And we want to weight interference and pops equally. And those of you who are mathematically sophisticated will know that that pretty much characterizes the formula that's up there on the paper. We were able to say this, and the lawyers scratched their head and said, well, that makes sense. And so this was a formula that worked pretty well in our simulations and seemed to make sense to the industry participants and to, kept things simple. Okay. To test how well this did, after the auction, we ran some simulations, and using to run simulations, you need values. We used some publicly available data sets to estimate what station values might be and did some randomization around them. We'd used stuff that had been published in the literature. And it was impossible for us to calculate Dickery auctions for the whole country. So we studied a subproblem around New York City, basically 500 miles around New York City, and used that as if that were the auction, and used that to test our methods. And here's what we found in the simulation results, that the computation time for this problem for an average Dickery auction was 90 CPU days for the CPUs we were using. And the computation for the clock auction using the software, our actual software, was 1.5 CPU hours. Okay, so that that's to establish for you that we did the computations fast, okay, that this is much easier to compute than optimization. The efficiency loss, well, the Dickery auction by definition is always efficient. It has a 0% efficiency loss. This is using as a denominator the value of the stations taken off the air, since most stations get left on the air. And this auction, which aimed to balance efficiency and cost objectives, had an average efficiency loss of 5%. The Dickery auction, if you call its cost index 100, the cost of the clock auction, which offered lower prices to smaller stations, was 76. It saved about a quarter of the cost. Remember, the total cost was $10 billion. So if this is representative, we saved about $3 billion in cost for the overall auction. So this was a big deal, being able to adjust for both. Okay. And this is my last slide, so given that we started a little late, I'm more or less on time. So one of the questions that economists like to ask about problems like this is, what do we need government for? Why couldn't the private sector just work it out on their own? This is a question I naturally, as you would have expected, I get whenever I give this lecture at the University of Chicago. And the answer is, why do we need any multilateral coordination at all? Why can't AT&T just buy the Chicago broadcast station or something like that? Why not just sell or give to the broadcasters the full right to use their spectrum however they want and allow trading to guide the allocation? And the answer I offer is that reorganizing the spectrum by moving all the broadcasters, those who continue to broadcast, those who stay on the air, those who go off the air, to satisfy all these constraints, that's a coordinated action problem. That requires everybody to plan and coordinate it together. This is not a bunch of bilateral moves that are simply improving. And the next question people ask is, okay, it needs a coordination problem, a redevelopment agency for the spectrum, if you will. Why does it need to be the government? Why couldn't we just have some private sector party be responsible? And this has been a serious proposal that some have made. Why couldn't we just have a private sector party do this? And the answer that we offer is that a successful intermediary has to have and exercise power to specify standards, what's reasonable interference, remember that 0.5%, to require broadcasters to relocate to different channels whether they want to or not, and even to renegotiate international agreements about cross-border interference. The U.S. ended up coordinating with Canada on this. They were unsuccessful in attempts to coordinate with Mexico. So this is pretty much a governmental kind of function. Okay, and so that was all for today. And so today was about the NP-hard calculations and about how we replaced the Dickery auction, the 7 weaknesses of what has been the world standard, so to speak, the Dickery auction. I gave you 7 reasons that it wasn't a good idea. And I showed you that we had an alternative design that overcame all of those deficiencies and gave up only a small amount of efficiency. The Dickery auction is unique in its ability to be incentive compatible and efficient. Well, we had to give up efficiency to do that, but not very much. And we saved a lot of cost along the way and satisfied all the other constraints. Tomorrow, if I may give you just a brief forecast, I'm going to connect to Marshall. And part of the reason I decided to stay focused on this auction is we had to decide how many channels to clear. We had to find not just prices, but quantities. And so far today I've talked about how we found an allocation with a fixed number of channels, how did we decide how many channels to clear, and how did we fix the quantity in addition to setting the prices. And that'll be the focus of what I'll talk about tomorrow. So thank you very much.